talk about quantum clocks.
Thanks, Charlie. So yeah, today I'm going to be talking to you about a project I did with my collaborators back in Australia. So Jared in the audience, as well as some of my experimental collaborators back at the University of Queensland. And for those who attended QTD in Vienna, you've already seen it in this talk. So yeah, I apologize in advance. But this project is part of quantum clock precision studied with a superconducting circuit. So I just want to give a bit of an outline of what I'm going to be talking about today. So firstly, the first part is going to be basically what those who attending QTD have seen, which is building a simple quantum clock using our superconducting circuit. I'm going to start by introducing this idea of autonomous quantum clocks, which has already been talked about by Jared a bit at the start. But the effect of measurement as well, is what Jared alluded to. And how you can go about making such a clock using a very simple superconducting circuit. And then we're going to look at two different measurement regimes that this clock is subject to, which corresponds to the weak measurement regime as well as the strong measurement regime. And this leads to very different behaviors in this quantum clock. Then after that, I'll talk a little bit about how you can introduce a kinetic uncertainty relation for this quantum clock, which allows you to bound the precision of the clock by something called the dynamical activity. Then part two is just going to be a little bit at the end, which is a little bit more provocative, which is just thinking about different kinds of clocks that we can actually study. So this is something I've been thinking about a little bit over the last couple of months after thinking a bit about time. So it's more a set of questions and ideas that I've had, so it's all half-baked. So, but I thought leading into a discussion time later, it might be interesting to discuss this further with everyone. So yeah, like I said, it's going to be a little bit speculative. So first, part one, building a simple quantum clock. So what makes a clock tick? Well, as Jared alluded to, there's quite a lot of processes that can actually make a clock tick. But in general, if you're thinking about a stationary set of thermodynamic properties, you basically need is some sort of thermodynamic gradient. This could be a temperature gradient, it could be some sort of chemical potential, but basically you want energy to flow from one system to another via some other system, which drives a oscillatory process. This is what Jared is called a limit cycle. But basically what this alludes to is that autonomous quantum clock, that's one that is generated by a process like this, is in a non-equilibrium steady state. That is, it's as energy flows at some constant current, it causes the system to oscillate at some repeated frequency. But basically what this just necessarily implies is that the repetition or the accuracy of those ticks is going to be bounded by the thermodynamic properties of that system. It's pretty intuitive that you can see how these two things would be connected. But if you're looking at a quantum clock, there's an additional part that you need to account for, and that's the effect of quantum measurement. So as your clock is spinning and you want to measure it, the effect of this measurement is actually going to lead to measurement back action, which will actually perturb the dynamics of the clock, and that's going to lead to possibly a bad clock. So in this talk, I'm solely going to be focused on this part of the clock. I'm not going to be focusing on an autonomous quantum clock. I'm just going to be looking at a system that oscillates and it's subject to quantum measurement, and we're going to be treating that oscillating process as a clock. But you could go and conduct a much more broader experiment and generate that autonomous process and account for those thermodynamic variables. Oh, and just before going ahead, this problem of autonomous clocks has been studied by quite a lot by the team in Vienna, as well as Mark and the team here in Dublin, as well as experimentally by Natalia's group over at Oxford University. So this is a big and interesting field, and it's actually great to be at a conference where we're all talking about time. So I'm going to refer explicitly to the precision of the clock and not the accuracy of the clock. And that's because I'm talking explicitly about measuring the clock. We're not talking about generating ticks, we're talking about the effect of what happens when you measure those ticks. But for those who are familiar with Paoli's work and the team in Vienna, it's defined in basically the same way. We're going to call it the parameter n, which is the precision, and it's equal to the average tick time squared divided by the variance in the tick time. So basically, a good clock will then be characterized as having a high expected tick time relative to a variance, a low variance. So basically, you want very repeatable tick tock, and you don't want fluctuations in those ticks and tocks. So how do we go about building a simple quantum clock? Well, and like I said, this one doesn't have to be autonomous. And if you just think about graduate level of the first thing you do in quantum mechanics, which is study Rabi oscillations. So Rabi oscillations, you just have some qubit that's spinning around the Bloch sphere, going from the excited state to the ground state. And you can see as a function of time, it's just going to go up and down between the excited and the ground state. What we want to do in this system is continuously monitor the state as it goes from the excited to the ground state. So we want to continuously monitor the expectation value of sigma z. But like I said before, we want to study the effect of measurement. So we want a system where we can actually control the strength of our measurement too. So we need an experimental platform where we can generate high fidelity Rabi oscillations while simultaneously controlling the strength. So to do that, we can use a superconducting circuit. In a former lifetime, I was an experimentalist. I'm not anymore, I'm a theorist. So I'm going to breeze over this like a good theorist. But basically the way this system works is we have a transmon qubit, which is in green, which is dispersively coupled to a coplanar waveguide, a superconducting coplanar waveguide, microwave, at microwave frequency. So yeah, you can see this is our qubit here, and in red, this is our superconducting circuit. And basically, you can model this system using a very simple Hamiltonian. Here we have a coherent drive of our cavity, which is driven at strength E. We have a Rabi frequency omega, and that's the Rabi frequency of the qubit. And this interaction here describes a dispersive coupling between the cavity and the qubit. So basically it couples the mean occupation, or the occupation of the cavity to the polarization of the qubit. You can model this system using a very simple master equation. So we've got here spontaneous damping on the qubit at a rate gamma, as well as photon leakage out of the oscillator at this end at a rate kappa. And yeah, this is just the standard Lindblad dissipator. So in our system, the qubit is going to play the role of our clock, and the readout over here is going to play the role of our measurement. So that was a pretty complex looking master equation for the most part. It involves two different quantum systems. But we can play a few tricks to actually simplify this model. So we can start by adiabatically eliminating the cavity mode. That's basically we're assuming the cavity dynamics are much faster than those of the qubit. And if we do that, we can actually remove that part from the master equation. We can then also assume, and this is motivated by experiment, the damping of the qubit is basically zero relative to everything else. And if you make those tricks, you can recast the master equation just in the qubit dynamics alone, where now you can see we have no A modes, we just have the qubit modes. And you can see what we have here is a delta term, which is the AC Stark shift. And then we also have this measurement strength kappa here, which is proportional to sigma z. And the nice thing is you can see now that our measurement strength here is actually proportional to the intensity of the drive of our cavity. So what this means is if we drive our cavity harder, we pump it harder, that'll actually lead to a stronger measurement of the qubit. And if we pump it less, that'll make it weaker. So by tuning the parameter of the strength of our cavity, the way that we drive it, we can actually tune the measurement strength. So now we've got this qubit model where we can actually do those two things I was talking about before. So yeah, the weak driving regime will correspond to the weak measurement, and the strong measurement will correspond to the jump clock. And I'll go into those two those two scenarios. So the oscillating regime, I'm going to call it oscillating clock, is when the measurement strength is less than half the Rabi frequency. So if you do a stochastic simulation using the unraveling of the master equation, what you can see is that the phase of the cavity is anti-correlated with the polarization of the qubit. So you can see these two are oscillating in phase with one another. So we're going to define, and you can see quite clearly now that as this is oscillating, the ticks and the tops are now becoming a random variable. So we're going to define a single cycle or a single tick-tock is going to be the difference, in this case, between for the signal to go through a full cycle, so from through a cycle of 2 pi. as Jared talked about earlier, if you're in this very weak oscillating regime, the distribution of the ticks is going to be given by this inverse Gaussian distribution, or the Wald distribution. And you can see here that we have our measurement strength in here. We have the tick time, and then you can see it also depends on the Rabi oscillation, the Rabi frequency. So given what we have, we can actually go through and compute our expected tick time and the variance, and then you plug that into the formula here, and you get a nice expression for the precision, which is this equal to 2 pi times the Rabi frequency divided by the measurement strength. And what's nice is, as the measurement strength increases, it leads to a worse precision in this clock, because the measurement strength gets bigger, it leads to measurement back action, which perturbs the clock. So what you can do now is you can go into the lab. This is what Eric and Prasad did for me. And you can actually run the experiment for many different Rabi frequencies. So here, all the different colors correspond to different Rabi frequencies. And you can go and calculate the tick distributions for different frequencies. So you can see the stars here correspond to a histogram of the different tick times. And what you can see is when the Rabi frequency is low, the tick times are longer because it's ticking slower. And you get this broader distribution. And then when the frequency is higher, you get a much sharper and narrower tick distribution. And when you go and you take all the experimental parameters that they've measured in the lab, and you plug that into the model, and you use the theory to calculate what you expect to see, you get these red distributions for the expected, this red line, for the expected tick time, the variance, and the precision. And what you can see is the black dots correspond to these estimates based on this data here. And you can see that the expected tick time follows the theory very well, but the variance goes a little bit off in this experiment. And you can see that actually leads to not a very nice precision. We should be getting this nice linear scaling, but it seems to taper off. This was because there was experimental parameters that we couldn't control. And unfortunately, when this data was being calculated, the experiment was being packed up and moved between labs, so we couldn't get more data. So we had to work with what we had. So that was the oscillating regime. There's now the jump clock. So the jump clock corresponds to the regime where the measurement strength is greater than half the Rabi frequency. And you can see now the behavior looks very different. So rather than having these nice oscillating cycles, you can see this kind of jump-like behavior, which Jared also spoke about in his talk earlier. The nice thing is, in this regime too, you can write down a distribution, that Jared also alluded to, of the tick distribution, which is given by a Poisson distribution. And yeah, so you can, and mu here is just again determined by the measurement strength, the AC Stark shift, and Rabi frequency. So you just play the same tricks again. You can then go and compute the expected tick time, the variance, and you plug it in, and you get this kind of paradoxical result where the precision of the clock is equal to 2. So in this case, what it tells you is that if you have a jump clock, it doesn't matter what the parameters are, its precision is always going to be equal to 2. It doesn't matter how hard you're driving it, or this, if you measure it stronger. If it's in this regime, it's always going to be equal to 2. So we go back into the lab, and we redo the same experiment for different Rabi frequencies. We get different distributions and different histograms. We plug them back into the theory and the experiment, and I just realized again I didn't fix that from the last talk, which I was supposed to put the numbers back on the axis. But you can see our experimental, our expected tick time is pretty close to what we would expect experimentally. It starts to deviate a bit, and the variance too is pretty close, but it starts to deviate, but which is nice in this case. They deviate in exactly the same way, so that they cancel and they're just bang on equal to 2, which is great. So yeah, this is a really, really nice, but it allows us to look at these two different regimes, the jump clock and the oscillating clock together. So just a summary so far, we can make a simple oscillating clock and a jump clock using a superconducting circuit. We can compute the measurement and the precision in both of these regimes too. But I haven't really talked about thermodynamics yet. I've just talked about making a clock. So when it comes to talking about thermodynamics, I'm going to look explicitly at something called a kinetic uncertainty relation, which is, this will become theory in 1 second. But firstly, what is a kinetic uncertainty relation? So for those of you who are familiar with thermodynamic uncertainty relations, you'll know that they're these nice bounds. They've been around for 2 decades now. How long have they been around for? 2015. Oh, it's 2015. Oh, maybe that's much quicker. But basically, the thermodynamic uncertainty relation allows you to put a bound on the signal-to-noise ratio by the entropy production. So it's quite nice. They've been extended to quantum systems as well. This is what you would see in classical systems. But basically, the kinetic uncertainty relation, something that's very similar, but it holds more generally because it holds in non-equilibrium steady state, but it also doesn't require detailed balance, which is an essential assumption for entropy production. And instead of being bounded by the entropy production, you're bounded by this quantity called K, which is the dynamical activity, which is basically a measure of how active the system is. So if you had quantum jumps, it would be the sum total of the number of jumps that occurs. And as you can see in our system, as we're measuring sigma z, we don't have jumps, we don't have detailed balance, but it's actually measured to the rate of measurement in our case. But how do we go and compute the kinetic uncertainty relation? Well, we can use it, we can calculate using these papers down here, and also Pascal's work, which has also been very useful in this context. But basically what you do is you start with a generalized Kramer-Rao bound. This is quite intuitive as well, because when you're thinking about a thermodynamic uncertainty relation or a kinetic uncertainty relation, you're talking about parameter estimation. You're trying to estimate the signal-to-noise ratio. At the end of the day, if you want to get the best bound of the signal-to-noise ratio or the variance or parameter estimation, you start with the Kramer-Rao bound. So basically this puts a bound on the variance, this quantity down here, which I won't go into a lot of detail, and the quantum Fisher information. But basically here, theta is an arbitrary parameter. And in our case, when you set theta equal to 0, it corresponds to the true system dynamics. So the way to understand this, sorry, I got a simulation. I thought that was on the last slide. So basically, what we need to do is we need to calculate these. All we need to do is to compute our kinetic uncertainty relation, we have to calculate the numerator of both those two terms. Because we had the variance, we just have to calculate this d theta term as well as the quantum Fisher information. So first thing we want to do is we want to calculate this term here. So basically what you do is you start by parameterizing all your system, all the rates in your equation by this parameter theta. So basically your Hamiltonian, you can scale it such that you get 1 plus theta times the original Hamiltonian, and your dissipators can be the square root of 1 plus theta times the original dissipators. What this does effectively is it scales all the rates in our system. So our Rabi frequency, our AC Stark shift, as well as our measurement rate. And the way you can intuitively think about this is when theta is greater than 0, it speeds up our system dynamics, it speeds up the clock. If theta is less than 0, it slows down the clock because the rates are lower. So by tuning, seeing how sensitive the change is to our system dynamics with this parameter theta, we can learn insight, we can gain insight into the quantum Fisher information as well. So if you plug this, if you calculate this quantity using the distribution for both the Wald distribution and the Son distribution, you actually show that this quantity here is equal to the negative of the expected tick time. When you square that, that just becomes the expected tick time as well. So the last thing you need to do is compute the quantum Fisher information. And this can be done using, in steady state, using perturbation theory. Again, I won't go into details here. But basically what you can show is the Fisher information in this case is given by the expected tick time times the dynamical activity plus this Q term. And like I said before, K is the dynamic activity. It's just equal to the measurement rate. And this Q term is what's called the quantum correction, in this case, or the quantum dynamical activity. And you can see we can get an answer for it analytically. And it is just determined by all the different rates in our equation. So you plug all this back into the Kramer-Rao bound, and you get this expression here, which you just flip over, and you get a bound on the precision in terms of basically the Fisher information or the kinetic uncertainty relation. So what you can do now is you can go into the oscillatory regime again, or the oscillatory clock, and you can calculate these two terms exactly. So we had our precision before, and we can now go and estimate this guy as well. And as you plug it back in, and you can see this red region will correspond to a violation of the KUR. The red dashed line is theoretically what we expect to see. But you can see that because our variance was so bad, it actually deviates from what we would expect to see. Likewise with the jump clock, you can plug all this back in and you can see that we actually get really nice agreement between what the theory predicts and what we measure experimentally. So basically we could actually go and calculate this KUR and test it experimentally for our clock, which is quite nice. So just to summarize so far, we can make an oscillating clock and a jump clock using our superconducting qubit. Measurement can impact the quantum clock's precision. So strong measurements lead to more perturbative behavior of the clock. We can compute and measure the precision in both regimes, and our clock satisfies the kinetic uncertainty relation in both of these regimes, and it allows us to bound the precision by the quantum Fisher information. So this was the team that was involved in this project. It was a fun project to be a part of, and there's more coming down the pipeline, which I'm not involved with but that'll be coming out hopefully soon. And then I've got a couple of minutes left, so I just want to go into part 2, which is just a very brief detour thinking about some different kinds of clocks. So in this talk so far, we've been focusing on a very particular type of clock, but as Jared mentioned to you earlier, there's a whole area of classical clocks, which is everything's classical. There's no issues really here. We can think about them as being pendulum clocks, grandfather clocks. Everything is well defined because we don't have this issue of quantum measurement that shows up. If you want to read more, you should go read Jared's contemporary physics article. It goes into this in a lot of detail. The clock that we were talking about today, and the one that I would argue has been primarily studied in the literature, is a quantum clock plus some classical readout in this setting. So in this setting, you have some sort of quantum clock that is interacting with another system, which then can be read out via some process, and then the ticks are then stored in some sort of classical register. In this case, the ticks are stored in a classical register, but the important thing is that dissipation and measurement is what breaks time reversal symmetry and allows you to define the clock. And basically, in this kind of approach, you are really looking at an open systems approach to quantum clocks. And like I said, basically the whole kind of field that I can think of so far has been in this sort of area. But this is kind of a hybrid clock when you think about it. So can we think more generally about quantum timekeeping? So I've used the word timekeeping and not clocks, because in this sense we're not really measuring ticks and tocks, but we are still talking about quantum systems that have some sort of notion of time. So timekeeping really is a relational process, as Jared alluded to before. So in the body, you have a million different kind of cycles going on. I'm not constantly measuring those cycles, but those cycles can be defined relative to each other, such that my body knows how time is being kept by the relationship between those two. So we think of clocks such that there's multiple oscillatory processes within the system, such that a notion of time does arise. It doesn't require dissipation, and it doesn't require a measurement process. In this case, timekeeping would be kept or stored between the relative oscillations between those two systems. And you might be wondering, how does this breaking of time reversal symmetry come into it? Well, this can be done coherently using things such as coherent feedback, or it can be done using circulars or nonlinear interactions. It doesn't require the notion of measurement to break that time reversal symmetry. Again, in this process, you don't need measurement, you don't need dissipation, but you do need some sort of initialization scheme at the start. So you do need to initialize your state. And you might need to read it out at the end in like one particular measurement. So it does require a 2-point measurement scheme, but the notion of time between those two systems is not defined by the dissipation itself. So the question I've kind of been thinking of, can we think of more general timekeeping systems within, and the thermodynamics of these clocks that really are in that setting truly quantum mechanical? So is measurement actually needed for quantum timekeeping in this sense? And what would such a quantum clock look like? So those are the 2 questions I wanted to kind of think about going forward. Thank you very much.
For the talk, we don't have any questions.
to get what you have in mind on your quantum timekeeping box.
Yep.
Do you have in mind that you are necessarily using this for control? So like you are developing a quantum system to time the action of another quantum system, or do you also have in mind a quantum clock which is keeping time on its own, and you can read out time for it, or the other way? So okay, do the first part, and I can like show on my second idea.
So thinking about it in terms of quantum control is a very natural way to think about it. Like you think your body, your heart is defined as basically a feedback system with relation to everything else that's going on. So the clock in itself could be used as a control for some other process. But I think when we think about control, there's a very human way for us to think about like we're trying to do something with these systems. Like, could we think of other systems that just interactions that are locked in such a way that this notion of time kind of emerges naturally? So,
yeah, thanks a lot for the talk, and especially for this thought-provoking last 5 minutes, which I think is very interesting. And I also have a question about this last point you mentioned, somewhere in relation to the page Wutter's formalism. So it reminds me very much of this formalism, but I assume you want to go somehow beyond this, say, theoretical construction. Can you explain what would be the difference between what you have in mind and page Wutter's formalism?
You need to remind me exactly off the top of the head the page Wutter's. It's slipping my mind right now. I know it, but I'm just remembering exactly what it is again. So I think it's somehow in this setting of relational dynamics where you introduce an auxiliary system that somehow you define to be this clock, and overall the joint state of whichever system you have and the clock is then time independent. Okay.
But I mean, yeah, we can also discuss later if other people have different questions.
Yeah, I think in that sort of way, I am thinking about different localized systems. So there are two systems. They have a joint state, they have some shared state, and their dynamics are evolving such that the notion of time between them is not. You're not specifically looking for one or the other, but the notion of time between them emerges. But yeah, maybe we can talk about it a little bit later. Off the top of my head, I need to go back and revisit what it is.
Yeah. Cool. Thanks a lot for the talk.
Yeah, thanks for the talk. It's a lot of interest in the last part of our presentation. So my question also goes there. I was just wondering, actually I was also chewing on this question during your talk, some shared deep question there about the role of the measurement. And so with your approach, with your last section where you thought, how could we go beyond the measurement-based work? I was just wondering what goes wrong with the naive approach that the theorists would take, which is instead of this, including the measurement as sort of textbook projection, I include ancillary system with which system interacts, and so in this way I introduce an interaction instead of the measurement, and so in principle it gets to something like in your box that I have a clock and another system, and they interact with just in such a way that mimics the action of the clock, but in this case it mimics really just because I reformulated the measurement that is picked up by another system. So what goes wrong with the...
Yeah, that's a good point. Because at the end of the day, when like it's kind of moving the Heisenberg cut, that's kind of it. So like, if we go back to it, like in this picture, this one here really just says I'm putting the Heisenberg cut at the end of my experiment, and I'm registering these as classical ticks. I'm going to define time relative in that sense. Where in this picture, you are really you have this interaction, but you're keeping it within the quantum system too. You're taking the Heisenberg cut from beyond the system as well. Where it goes wrong, I'm not sure. This is like a very half-baked idea still. So it's something that I've been thinking about, but I haven't got a very, as you can see, Jared, you might have a suggestion?
Yes.
Yeah.
I'll wait for another question.
But I guess like the reason why I was thinking more about these systems as well, like where you have coherent feedback, or say a circulator, which in itself does allow you to create an interaction which does break this time reversal symmetry, but doesn't require this dissipative process, dissipative movement.
Okay, maybe one more question.
And just a very short question. Is there any good use for this clock which does these jumps and always has n equal 2? This is just a demonstration of principle.
So you weren't referee C, were you? We got a lot of questions from the referee being like, how is this useful?
I'm sorry.
Yeah.
I want to ask why it's 2 and not 1.
Yeah, well, that's a good question. Why it comes out to be 2? I'm not actually sure. I guess, yeah,
it's like
that's true,
averaging
yeah.
over 2
Yeah.
events.
Yeah.
And well, you want to make your last comment before to the discussion session?
Yes, so first of all, jump clocks. Yes, that's regarded as thermal time hypothesis, so they may have applications in quantum gravity. Coming back to this question, there's all control in classical stochastic control theory is measurement-based control, because different systems actually have values that we discover in the back. But in quantum control, measure-based control is distinct from another kind of irreversible process called coherent control, where you put in circulators and you take the field out of some system, which is a complex dissipative process, produces an output field. You run it through a circulator, you run through a few more systems, so it never comes back. But you just make a big long circuit around and bring it back and drive the thing you started with. And that enables you to do feedback control that you could never do by measurement control, such as simultaneous measurement of position and momentum. So there's a way to implement coherent control that looks like simultaneous measurement of position and momentum that you can't do with measurement-based control. So it's relatively easy to see how you would, really easy to make clocks using coherent control, and that's the experiment that Michael alluded to that we're doing at the moment. They are irreversible, they still dissipate energy, but they're not based on measuring a clock signal. That's not how they work. True, you have to initialize them and check that they're calibrated correctly, but they're based on doing this coherent feedback process. It's irreversible, though.
Yeah.
Yeah.
I guess that's the difference between these two as well. What's the notion? Where does that irreversibility come from? Does it come from a dissipative source, or does it come from some coherent mechanism that is still irreversible?
Well, ultimately, there has to be a low temperature reservoir somewhere to do coherent control, because otherwise you just add more noise to the system and you try to take it out.
Yeah.
Okay. I think that's the perfect start for a good discussion session. Let's thank Michael.